Hi everyone, this is going to be another little review video on some linear algebra topics. So I want to start with basics. The first one is going to be thinking carefully about matrix vector multiplication. So let's suppose that A is an m by n matrix. Okay, so this means that A has m rows and n columns. So what does this tell us about matrix vector multiplication? So this means that A is m by n. V must be an n by 1 in order for this multiplication to make sense. And so this total product is going to be m by 1. So let's see how this two ways to look at matrix vector multiplication that are very useful. So one is thinking about what V does to the columns. So I'm going to write A out in terms of its n columns. I'm going to call capital A1 the first column, capital A2 the second column, capital AN the last column. So one way to think about what AV does is each entry of V multiplies the corresponding column of A. So AV is A times V, V1 up to Vn. Remember that matrix vector multiplication goes like that. So that means that this is equal to the column vector A1 times the scalar V1 plus the column vector A2 times the scalar V2 up to the column vector AN times the scalar Vn. Okay, so now let's think about a different way to think about matrix vector multiplication in terms of the rows of A. So let me write A now in terms of its m rows. We call this little a1 to help us remember that it's different from capital, which I was using for the columns. Okay, and so AV is now A1 up to AM times V. I'm not going to write out the entries of V on purpose here, you'll see in a second, because what this is equal to is the vector that has m components. The first component is A1 dot product V. The second is A2 dot product V. AM dot product V. This is basic, but very useful to think about these two different views. So just a very brief example. Let's suppose A is the matrix 1, 4, minus 2, 3, and V is the vector 1, 2. Then AV is equal to, in the first view, it's the column times the first entry of V plus the second column times the second entry of V, which is equal to 1 minus 2 plus 8, 6, which is 9, 4. And the second view, AV is equal to the dot product of 1, 4 with 1, 2, and the dot product of minus 2, 3 with 1, 2, which is equal to the dot product of 1, 4 and 1, 2 is 1 plus 8, which is 9. The dot product of minus 2, 3 with 1, 2 is minus 2 plus 6, which is 4. And of course, these two numbers agree, which would have been a problem otherwise. Okay, let's move on. The next topic I want to talk about is Euclidean norms. The Euclidean norm. This is just a fancy word for distance. Okay, so if I have the vector 2, 3, so that would be this vector. What is its length? Well, it turns out that there's various ways to define the length of the vector, but Euclidean really means we measure the length as you would measure it if I marked out this distance on a field and I asked you the distance between this point and this point, you would just measure this length. And by the Pythagorean theorem, this is equal to this squared plus this squared. So let me call this distance z, and this x1 and x2. So the Pythagorean theorem tells us that z squared is equal to x1 squared plus x2 squared. And therefore the length, z, is equal to the square root of x1 squared plus x2 squared. This is exactly the definition of a Euclidean norm. We can define it in 2 dimensions, just like I did here, or in higher dimensions. And the notation is as follows. If I have a vector, let me write my vector to be vector x with components x1 and x2. I'll denote its Euclidean norm. It's denoted by these 2 double lines. This x is a vector here, with a subscript 2, and it is equal to the square root of x1 squared plus x2 squared. We can also define this in more dimensions. So in 3D, if my vector x has 3 components, x1, x2, x3, then its Euclidean norm is the square root of x1 squared plus x2 squared plus x3 squared, and so on. And of course we can define it in n dimensions as well. If x is equal to x1 all the way up to xn, then x2 is equal to xi squared, the square root of this thing. Some other notation here. Remember that the dot product between 2 vectors, x and y, x transpose y, is just the sum of xi, yi, where x is as above, x1 to xn, and y would similarly be y1 to yn. So this means that I can now write this Euclidean norm of x as the square root of x transpose x, which is the same as writing that this Euclidean norm squared is just x transpose x. So let's look at this exact definition with matrix vector multiplication. So this means that if, again, A is, as above, an m by n matrix, and x is n by 1 vector, in other words, some notation that here x is an Rn, then ax squared. Let's think about how we can write this in the 2 ways that we've seen. And so this is going to be the sum of the entries of this m long vector, each squared. So this is the sum of the first entry squared. So what is the first entry of the vector ax? Okay, so this is where it's helpful to think about the 2 different ways of matrix vector multiplication that we discussed just a second ago. So let me scroll up so we can see that. And here we go. So the first view was in terms of the columns. So this is not very particularly helpful. This doesn't, I still have to do calculation to figure out what the first entry of this vector is. It represents AV as a sum of a bunch of vectors. But in the second view here, now at the center of the page, I see that the first entry of AV is the dot product of the first row with all of V, and so on. Okay, so let's apply this to the setting So this is the sum of the entries. So it's the sum from I equals 1 to m entries. And it is AI dot product x. This is now a scalar, and it's this squared. Okay, so that's one view. The other possible way to write this is using this x transpose x notation. So we can also write this as ax squared is equal to ax transpose times ax. So this is using exactly this correspondence here. I'm going to delete these lines so the page doesn't get too cluttered. Okay, now what is AX transpose? So let's remember that when we take a transpose, it reverses all of the orders. So this is equal to X transpose A transpose times AX, which is equal to X transpose AX. So these two things are exactly the same, and they are scalars. So let's see why they are. It's clear that this top view is a scalar because it's just the sum of numbers. But let's just double check, do a sanity check here, and make sure that these are. See what the dimension is of this. So x is n by 1, so x transpose is 1 by n. A is m by n, so A transpose is n by m. A is m by n, and x is n by 1. Therefore, this whole thing is 1 by 1, which means that it's a scalar, or just a number. The final thing I want to remind you of is a little bit of calculus with vectors and matrices. And I just want to show you one specific rule. So in 1D, this is something that we all know, ax squared, if I have this function, if I take the derivative of ax squared, this is equal to 2ax. But in more dimensions, we have something perhaps more interesting. In n dimensions, I may have the function, and this is very useful for what's called multiple regression, x transpose, A transpose, AX. Okay, so this is just a vector times a matrix times a vector. Just exactly what we had above. And this is now a function of n variables, x1 all the way up to xn. And so I could ask for its partial derivatives. In other words, its gradient. So let me write this out formally here. F of x1 to xn. This is equal to x transpose, A transpose, AX. And if we scroll up, you'll see that I could also write this as the sum of the rows of A times the vector x squared. And I want to take the partial derivatives of this. So remember that the gradient of a function is a generalization of its derivative. So it's the vector of all of its partial derivatives. And the notation for the gradient is this. So this is the vector whose first entry is the derivative of f. We use this symbol instead of d because it's the derivative only with respect to one of its variables when you treat all of the other variables as other constants. Its first entry is this. Second entry is the derivative with respect to the second variable all the way to a derivative with respect to the last variable. So if you remember your single variable calculus, you could just write out this expression in terms of x1 to xn and do all of those painful calculations. But we're going to do a little bit of little bit of shorthand here to see how you can compute this directly. And you can just memorize this as a rule if you like. But for f equal to x transpose AX, f of x, I should be a little more careful, the gradient of f of x is equal to twice A transpose AX. So you can see the similarity here between the rules for just single variable and for gradient. And we're going to be putting all of these things together.